Hello everyone. Today we are going to explore another important concept used in test benches, that is the cloaking block. When you build a verification environment, then definitely you will deal with timing challenges. Means when you need to sample your signals and you need to drive the values. So this is where system Verilog's cloaking block comes into picture because it helps you in coordinating the signal activity with the clock, and thus it makes test benches more predictable and more timing accurate. So let's understand what a clocking block is, why we need to use it, and how it simplifies our verification environment. So this is a quick look at the agenda for this session. So we will start with a brief introduction to clocking blocks, what they are and why they are needed in the system Verilog. Next, we will talk about purpose and benefits, like how clocking blocks helps in improving the timing control and avoid the race conditions. Then we will go over the syntax and the structure of a clocking block and see how it is written in the code. After that, we will explore the features that clocking blocks offer. And next, we will understand the concept with a simple example use case, and we will see how a clocking block is typically used. Then we will highlight some common pitfalls that new users face and share best practices for using clocking blocks effectively. Finally, we will wrap up with an assignment. Have you ever faced race conditions while driving or sampling signals in a test bench? And I guess answer to this question is yes. And that's why you need a cloaking block in your test bench. So cloaking block is a construct that provides a way to synchronize signal sampling and driving in a test bench relative to a clock. So it basically defines the timing relationship between the signals and the clock, and defines when input signals should be sampled and when output should be driven. So basically it is a synchronization mechanism, and it makes sure that the test bench components observe signals at the right time, and thus they avoid the race conditions. So these clocking blocks are mostly used in test benches, and because we isolate it, I mean we separate the timing concerns, we write it separately in a clocking block, so it simplifies the test bench code and makes it more readable and maintainable. So this is example shown here. Here we are defining a clocking block named CB, and it is triggered on the positive edge of the clock. So here we are applying a default input skew of 10 nanosecond and output skew of 2 nanosecond. So we will understand the syntax in further slides. So in short, I will tell you that cloaking blocks helps in enforcing the timing discipline, and they avoid race conditions, and they keep your test bench code neat and clean. So let's see the purpose and some of the benefits of using clocking blocks in SystemVerilog. So the main purpose of a clocking block is to abstract the timing details for signal sampling and driving. Thus it ensures consistent and predictable behavior in test benches. Now for benefit side, it eliminates race conditions between the DUT and the test bench by aligning the driving and sampling of signals properly. It simplifies timing specification, means test bench does not need to manually control the timing for each signal. The clocking block ensures that the signals are driven at the right time, and thus it ensures faster operation. It also improves code readability and reusability because this timing behavior is defined separately. Now let's understand the basic syntax of a clocking block in SystemVerilog. So clocking block starts with the clocking keyword followed by the clocking block name, and it ends with the end clocking keyword. So here we are defining a clocking block named CB underscore name. After that we specify the clock event. So here we are defining the clock event, that is the positive edge of the clock. So this whole block triggers at the positive edge of the clock. So this it can be any event. Next we specify the input and output skews. So clocking skews specify the moment at which input and output clocking signals are to be sampled or driven respectively. So here in this case we are setting input skew as 1 nanosecond, means inputs are sampled 1 nanosecond before the clock edge, and output skew as 2 nanoseconds, means output should be driven 2 nanosecond after the clock edge. Next we are listing a few signals for sampling and driving. So these are the signals which are synchronized with the clocking block, and each of these signals can optionally override the default skew values. So in clocking block we mainly have three parts. First is the clocking event, next is the clock skew values, and next is the clocking signals which are synchronized with respect to this clock. So now let's understand the concept of input and output skews in clocking blocks, because applying skews correctly is very important because it ensures proper synchronization and it avoids race condition in simulation. So firstly, note that skew must be a constant expression and it can even be set as a parameter. When input skew is specified, it means signal is sampled at skew time units before the clock event. So it means the test bench samples the DUT output before the clock edge, before the rising or falling edge of the clock, whatever event you specify. So effectively there is only one cycle delay from DUT output to the test bench input, and thus it allows safe sampling. If output skew is specified, means our signal is driven skew time units after the corresponding clock event. So in this case, the test bench drives the DUT inputs right at the clock edge, and there is no delay, there is no artificial delay between the test bench output and the DUT input. There are multiple ways a skew can be specified in a clocking block. So first is this hash D. So here the skew is D time units, and the actual time unit depends on the time scale of the block or the module. Next is hash T nanoseconds. So D is directly given in the nanoseconds. So this is explicit and it avoids ambiguity from the timescale settings. Next is this hash 1 step, and it means the sampling is done in the preponed region of the current simulation timestamp. So these are the default values, skew values. If no skew is mentioned explicitly, then SystemVerilog sets the input skew to basically one time unit and output skew to 0 by default. You can see in the diagram also like how input is sampled before the clock edge and output is driven after the clock edge. So basically this control over timing is very helpful in creating accurate and race-free test benches, mainly for synchronous designs. Now let's explore some of the key features of the clocking blocks in SystemVerilog. Firstly, skew allows us to fine-tune the timings for sampling inputs and driving outputs. Next, signals in a clocking block can be referenced hierarchically. For driving and sampling, you can use @CB underscore name. CB underscore name is the clocking block name. So you can directly use this name in procedural blocks to synchronize activities with the clocking block's timing. Next is program block integration. It is a common use case. So clocking blocks are mostly used inside program blocks, which helps in avoiding the race conditions with the design. SystemVerilog supports multiple clocking blocks, so it is mainly useful when you are dealing with multiple clock domains in complex designs. And lastly, each clocking block is associated with only one clock. Now let's look at a simple example to understand how clocking block is used in the SystemVerilog. So here, firstly, we are defining an interface named intf, and it takes clock as an input. So inside this interface, we are defining some control and data signals, and then comes the clocking block CB. And this block is triggered on the positive edge of the clock. Next, we are defining some input skew and output skew values. So input skew is 10 nanosecond and output skew is 2 nanoseconds. Next, we are declaring which signals are output and which are input from the test bench perspective. Then we are defining the mode ports. First is the mode port for design. So it is used for connecting with the DUT. And next we are defining the mode port for test bench, and it connects the clocking block with the test bench. On the right hand side, you can see a small portion of the test bench, and here the clocking block is being used to drive the signal. So here we are using this interface dot this TB mode port, and this statement, this line writes to the read signal. See, this read signal is defined as output in this mod port TB. So this line writes to this output signal synchronously, means with respect to the clock, and it uses the output skew value defined in the clocking block. So here you can see the clear separation between how the signal is declared, how the direction is specified, and how we can specify the timings in a clocking blocks. So now let's understand another practical use case of clocking block. So here in this example, we are verifying a simple D flip-flop, and it ensures D is driven and Q is sampled at correct times, means at the right moment. So now let's go through the code. So here we are defining a module test bench and declaring the signals clock, D and Q. Next we are defining a clocking block. So we are defining a clocking block inside a module. So please note that this clocking block we can define inside a module, inside interface, or even inside a program block. So here clocking block is defined on the positive edge of the clock. We have set the default input skew to 1 nanosecond and output skew to 0 nanoseconds. Then we are defining a signal, input and output signals, and they would be synchronous with respect to clock. Now here we have defined two initial blocks. In the first initial block, we are toggling the clock after every 5 nanoseconds. In the second initial block, we are using this @CB. So this is the clocking block name. So we are using this event to synchronize with the clocking block event. So here cb.d equals to 1. It drives the value onto D using the clocking block. And next we are using the $display statement. So it samples the value of Q, again using the timing of the clocking block. So this use case shows how clocking blocks helps in signal driving and sampling operations with respect to clock, and thus make our test benches more deterministic, predictable, and more reliable. Now let's look at some common pitfalls and best practices while working with SystemVerilog clocking blocks. So one of the most frequent issue is incorrect skew values. So this can lead to timing mismatches and race conditions in simulations, mainly when signal sampling and driving are not properly aligned with the duty clock. Next is another common mistake is mixing clocking block signals with non-clocking signals. And lastly, many users forget to use @clocking block event for synchronization. So if you don't use this, so this would defeat the purpose of using a clocking block altogether and can lead to improper timing behavior in test benches. Now let's talk about best practices. Always use meaningful names for your clocking blocks and make sure to align your skew values with the DUT timing requirements. Always it is a good idea to place your clocking blocks inside the program blocks. And finally, always verify your clocking block behavior using waveform debugging. So by avoiding these pitfalls and following these best practices, we can write much more robust and maintainable test benches in SystemVerilog. Now this is a small assignment that will help you apply what we have learned about clocking blocks in a practical scenario. So here you have to verify a 4-bit synchronous counter module in SystemVerilog. So this counter increments on every positive clock edge, but only when enabled signal is high, and it resets to 0 when the reset signal is low. This reset is basically active low synchronous, which means it triggers only on the clock edge. Next, you have to create a test bench that uses a clocking block to avoid race conditions between the DUT and the test bench. And to check the counter's output, basically you have to apply a stimulus from the test bench, and you need to check the counter output to ensure it behaves correctly across different conditions. So here are some of the constraints for the clocking block. Firstly, it should sample the input 1 nanosecond before the clock edge. Next, it should drive the output 0 nanosecond after the clock edge, and it must be defined inside a program block which ensures proper separation from the DUT and supports proper timing scenarios, semantics. In case of any queries, questions, or need any clarifications, you can contact me on this mentioned email ID, or you can connect me via LinkedIn. Thank you.